Okay, continuing with chapter 18. We've talked about enthalpy and the endothermic being a positive delta H, exothermic being a negative delta H, and that exothermic reactions are favored. Thermodynamics favor an exothermic reaction, yet we know endothermic reactions are spontaneous. The second law of thermodynamics states that for a process to be spontaneous as written, and as written would mean in the forward direction, okay, where the reactants are on the left, products are on the right, the delta S of the universe must be positive. And the way we calculate the delta S of the universe, it's the sum of the delta S of the system and the delta S of the surroundings. And now the system is going to be the delta S of your reaction. The way you could calculate the delta S of the system is using the formula we introduced earlier, where you take the sum of the entropies of each of the products, and you subtract out the sum of the entropies of the reactants. And where the N and the M are the coefficients, and you're looking things up in the appendix. And again, the system is the reaction. To calculate the delta S of the surroundings, and it was discussed in a previous lecture just with the sign, whether it's positive or negative. But if a process is exothermic, that releases heat. That's going to cause the surroundings to warm up. So releasing heat is going to result in an increase in entropy, okay? Because the delta H would be negative if the process released heat. And this formula would mean the delta S of the surroundings would be positive. So the formula to calculate the delta S of the surroundings is this. The delta S of the surroundings is equal to the negative enthalpy change for the reaction divided by the temperature. And typically in this, the temperature, well, not typically, but it needs to be in Kelvin. Also, be reminded that enthalpies are usually large energy transfers, so they're in kilojoules. But entropies are usually small amounts of energy transfer, so they are typically in joules. So you just have to watch your units. When you're doing this calculation, the entropies in the back of the book are going to be joules. When you're doing this kind of calculation on an enthalpy, it's going to be kilojoule. So if ever you're doing this, just watch that enthalpy and entropy and be sure the units are matching. Okay, so previously we had used this equation that hydrogen and chlorine produce hydrogen chloride. Okay. And that was one because you had 2 moles of a gas on the reactant side and then 2 moles of gas on the product side. We could not predict what the entropy of that reaction would be. But I believe we did calculate it using the thermodynamic data from the back of the book, from appendix. And the entropy change for this reaction is 20 joules per Kelvin times mole. So it is positive. The entropy of the reaction looks like it would be a spontaneous process. But if we note, the second law says that for a process to be spontaneous, the entropy of the universe must be positive. Well, all we've calculated at this point is the entropy of the system. So, to go more in depth on the signs of these, and we talked about it last time, you can have where the system and the surroundings are both positive. Okay, that will obviously give you an overall entropy of the universe as being positive. There can be a situation where the entropy of the system is positive and the surroundings is negative. But for the process to be spontaneous, this is going to have to be a bigger number. You can have a situation where the system entropy is negative and the surroundings is positive. Again, this would be the larger number and result in an overall spontaneous process. But you can never have both of these being negative. That's what the second law says. The system and the surroundings can't both be negative. So, let's look at this reaction and let's calculate the delta S of the universe. Okay? We know that the delta S of the reaction, the system, it's a positive 20 joules per Kelvin times mole. Okay, so to calculate the delta S of the surroundings, we are going to use this formula. Okay, and we're going to do this calculation at 0 degrees Celsius, which would be 273 Kelvin. And so what I'm going to do is go to the back of the book and look up the delta H's for each component of the reaction. And I encourage y'all to be comfortable using the appendix in the back of your book, okay? Because you're going to have to do that on the test. And you certainly don't want to wait till the test when that's your first time to ever try to look things up and get acclimated to that table. Okay. The enthalpy of formation for HCl is a negative 92.3 kilojoules per mole. And, I mean, you might want to go ahead and check what Cl2, the enthalpy change for Cl2 and hydrogen. But guys, do you recognize that hydrogen and chlorine are elements? And if you'll remember, enthalpies of formation for elements, remember that from Chem 1, they're always 0. So in doing the products minus reactants for this equation, if the enthalpy of formation of HCl is negative 92.3 and there's 2 moles of it, we can see that the delta H for this reaction is a negative 184.6 kilojoules per mole. That's the delta H, but the formula has a negative in front of it. And we're going to divide that by 298 Kelvin. So obviously this is going to be a positive answer for the delta S of the surroundings. And this calculation gives me 0.619 kilojoules per mole times Kelvin, or Kelvin times mole. So if the system's a positive 20, and we know both of them are positive now, and the surroundings is a positive 0.619, I have to be careful because the surroundings, it's in kilojoules at this point. And in order to get the universe, I'm going to have to add these two numbers together. So 0.619 kilojoules is 619 joules per Kelvin times mole. So the entropy change of the universe is a positive 639 joules per Kelvin times mole. So this is overall a spontaneous process. Even though the delta S of the system was very small and it was hard to predict the delta S of the system, because this is a rather exothermic reaction, the delta S of the surroundings is large enough that this is a spontaneous process. Okay, so at this point, we will introduce the third law of thermodynamics. which says that the entropy of a pure crystalline substance at absolute zero, okay, is zero. What is absolute zero? You know, in math, absolute means you can't go below zero. Absolute zero is 0 Kelvin, which is theoretically the coldest temperature that could ever be reached. If you have a pure, perfect crystalline substance, and that substance is at 0 Kelvin, the entropy of that substance is 0. So see, unlike what we just did, enthalpies of formation of elements are 0. But entropies of elements are not 0, because there's always movement of the molecules, movement between the bonds. Even if it's a perfect crystalline substance, if there's vibrations and movements, there's entropy. But at absolute zero, all of those movements and vibrations cease, and so there would be 0 entropy. And the third law has never actually been tested, in that no one has ever reached 0 Kelvin. Labs have come close. It does have to be done in a lab environment. But nobody has ever dropped anything down to absolute zero. Okay, so what we just saw, that to truly predict the spontaneity of a reaction, you would have to calculate the delta S of the universe, which requires you to calculate the delta S of the surroundings. However, usually the measurements that are made are only about the system. So there is a thermodynamic function that allows us to just make measurements about the system to predict spontaneity. And that function is called the Gibbs free energy. And this process is derived in your book. This is actually starting section 18.5 in your book, but without deriving it. The Gibbs free energy, symbol for that is G. Often it's called free energy. The units for free energy, these are going to be kilojoules per mole. Okay, and the formula for Gibbs free energy is delta G is equal to the delta H minus T delta S, where of course delta H is the enthalpy change, delta S is the entropy change, and the T is the temperature in Kelvin. And these values would all be about the system, or for the reaction. Okay. A negative delta G says that the reaction is spontaneous. A positive delta G guarantees the reaction is not spontaneous. And when delta G is equal to 0, what does that say? It says that the system is at equilibrium. Okay, so if we examine this equation, and you want, as I go through this, keep these in mind. Delta G negative means spontaneous. Do you see that? If the delta H is negative, and the delta S is positive, okay, we know a negative delta H favors spontaneity and a positive delta S favors spontaneity. But do you see that if those are the signs of the H and the S, that the delta G will always be negative? Mathematically, that equation works out so that delta G is always negative. That means the process is always spontaneous if those are the signs of H and S. Okay? If the delta H is positive and the delta S is negative, what would that mean? Mathematically, that means the delta G will always be a positive number. So it's always non-spontaneous mathematically, no matter what the value of the number is. Okay? If the H is positive and the S is positive, what would it take to make the G negative? What's it going to take to make G negative to make the reaction be spontaneous? It's going to take a high temperature. So the reaction is spontaneous at high temperature. So see, if T was high enough and this value was positive, then when you subtracted it, it would make the delta G negative. Okay? What if delta H was negative and delta S was negative? How is that going to be spontaneous? Well, if ultimately you're going to subtract a negative number, then y'all know that would change the sign of it. So the delta G could be negative at very low temperatures. That means the reaction could still be spontaneous at low temperatures. Okay, so let's look at how we can use this about calculating the temperature. And to do that, I would like to examine this reaction of the breakdown of calcium carbonate. On heating, calcium carbonate will decompose into calcium oxide and carbon dioxide gas. Okay, and if you'll remember on your take-home test, environmental chemistry test, do you remember anything about this? About quicklime, calcium oxide, and it was used to purify the exhaust in industrial processes to control the amount of SO2. They would inject the calcium oxide into the purification chamber and it precipitates as calcium sulfite. So the reason I'm asking you guys to recall that is because this is an important process that needs to happen industrially because we need calcium oxide in industry to purify those exhausts. So how do they get calcium oxide? Typically, it's produced by decomposing the calcium carbonate. Okay, so we are going to calculate the delta G for this reaction using this formula. And we're just going to do it at 25 degrees Celsius using the data from the appendix. So in Appendix 2, I'm going to look up the numbers and calculate the delta H for the reaction and calculate the delta S for the reaction. And I think it would be a good idea for you guys to pause the video and you look up those numbers in the appendix and then pick back up and see if your numbers match mine. Okay, hopefully hopefully I looked up the right numbers and it matches what you guys have. So to calculate the delta H of the reaction, we're going to sum up the products for delta H. Those are the products. We're going to subtract the reactants, so we're going to subtract a negative number. And so for the delta H of the reaction, I get 177.8 kilojoules per mole. Then I'm going to also do that for the delta S. I'm going to sum up the products. And I'm going to subtract out the reactant, so subtract the 92.9. And so for delta S, I get 160.5 joules per Kelvin times mole. And so we know we're looking at both of these numbers are positive, and based on what we said here, this reaction is only going to be spontaneous at a high temperature when they're both positive. So let's calculate the delta G at 25 degrees Celsius. So the delta G is going to be the delta H, which is 177.8 kilojoules per mole, minus T, which is going to be 298 Kelvin. And what do we have to put in for S? Because we're going to take a number that's kilojoules per mole, and we've got to subtract a number that has the joule unit, but it's got to be the kilojoules. So here's where I'm talking, you have to watch those units. So that's going to be 0.1605 kilojoules per Kelvin times mole. Let me calculate that number. And I get that the delta G is 129.971, so we'll just say 130, rounding it, kilojoules per mole. It's a positive number. It's not spontaneous because and we knew it wasn't going to be because that it wasn't going to be spontaneous. We knew it would be positive because the delta H and the delta S were positive. But as I said in going into this problem, this is a process that has to happen in industry. Calcium carbonate must be decomposed to calcium oxide to control the SO2 emissions. So we know that if they're both positive, it's spontaneous at high temperature, but what constitutes a high temperature? So let's ask another question. At what temperature, this is going off of that same calcium carbonate problem, at what temperature will the reaction become spontaneous? Okay, and I'm going to transfer all of our information over. The delta H for the reaction is 177.8 kilojoules per mole. The delta S for the reaction is 160.5 joules per Kelvin times mole. So we know going into it, they're both positive. It's got to be at high temperatures. Now, I'm going to derive what we have to do here because you know this formula. And y'all know that the turning point of whether it's spontaneous or not is delta G positive or negative. Okay? And the turning point for that is 0. Okay? Because obviously below that it would be negative, above that would be positive. So I'm going to plug in 0 for delta G. Solve for temperature, y'all. Get temperature by itself. To get temperature by itself, I would add this to both sides. And then I would divide both sides by delta S. And I have temperature by itself. So when the problem says at what temperature will the reaction be spontaneous, this is the formula I use. And I just plug in the delta H's I have, again, watching the units. It doesn't matter if they're both in kilojoules or both in joules, but they have to be the same units. Whether they're both kilojoules or both joules, it's going to give you the same answer for temperature either way. Okay? And now I want to say over here that some of you, had we been in class, some of you would have asked this. why did I convert when I did these? And I started out with the kilojoules and joules. Could I have converted the delta H to joules? Because what I did is converted the S to kilojoules. And yes, I could have. But typically, y'all, Gibbs free energies are in kilojoules. Had I converted this to joules, my answer would have been 129,900 and something. And that's just a big number. So it's not wrong if you do it in joules. It's just that the convention of free energy is typically kilojoules. And that's usually clearly asked, like calculate the free energy in kilojoules. Okay, so again, it's not wrong. It's just easier numbers to work with when they're smaller in terms of kilojoules. So since I've already converted everything to kilojoules before, and I see that right here, I wrote this wrong. That should be 160.5 instead of 1,605. Okay, the delta H is 177.8 kilojoules per mole. I'm going to put the delta S in kilojoules as well. Again, there's 1,000 joules in a kilojoule. 0.1605 kilojoules per Kelvin times mole. And so what happens is the kilojoules cancels, the moles cancels, and I'm left with an answer in Kelvin. And my temperature Kelvin, it is a big number, is 1108 Kelvin. So for this process to be spontaneous, the temperature has to be very high. Now note, at this temperature, that's the point at which the delta G just becomes negative. So actually, to check this, if you plug that temperature in, let's see, 177.8, I'm going to leave off units, minus that temperature, 1108 Kelvin. I know, I put the units on there. We said at that temperature it should become spontaneous. In other words, the delta G should become negative. So, and the value of delta G is negative 0.034. Kilojoules per mole. So it is negative, y'all, but it's very small negative. So see, the higher the temperature you go, the reaction's going to increase its negative in delta G, and that's going to favor the product formation. Okay, so 1108 Kelvin, it's spontaneous, but the products are not largely favored. I'm stumbling all over my words this morning. Moving on to section 18.6, which deals with free energy. And equilibrium. And this is, I feel, rather simple. You guys know that when you have that little degree symbol on stuff, it means standard states. And so these two values are not the same, okay? When you're talking about a standard state, you might recall that has to be 1 atmosphere pressure. That means all the gases reacting are at 1 atmosphere. It has to be carried out at room temperature, 25 degrees Celsius. And it also means that everything has to be 1 molar concentration. Okay, so that's typically not the case for a reaction. You might start out at 1 atmosphere, but once the reaction starts going, those concentrations change. So everything you're looking up in Appendix 2 is standard state. Okay, it's like a perfect state, if you will. So it's actually the sign of the delta G is really what determines spontaneity, not the sign of the delta G standard. although that's typically what we can calculate. The delta G standard gives us an idea of the equilibrium constant. But I want to introduce this formula. The delta G is equal to delta G standard plus RT times the natural log of Q, where R, it is the ideal gas constant. And you remember that the ideal gas constant is 0.0821 liter atmosphere per mole times Kelvin. Okay, this is the same R, but the units are different because we need joule units in them. So the number's been converted, but the value of R is 8.314 joules per Kelvin times mole, or that value would be 8.314 times 10 to the minus 3 kilojoules per Kelvin times mole. Of course, T is still temperature, and you guys know that has to be in Kelvin. And Q, we've used Q before. Hopefully you remember that Q stands for reaction quotient. And if you'll remember also that the reaction quotient, it's just like an equilibrium constant. It's the product's concentration over the reactant concentration, and it's raised to the power of the coefficient. Okay, so let's work a problem using this. For this reaction, oh, that's too light. The equilibrium constant for this reaction is 0.113. What does the P mean? It means it was calculated using pressures. The standard free energy change with this equilibrium constant is 5.4 kilojoules per mole. So let's calculate the delta G and predict the direction the reaction is moving. To establish equilibrium. If the initial pressure of N2O4 is 0.453 atmospheres and the initial pressure of the NO2 is 0.122 atmospheres. Okay, see if you can use the equation I just introduced to calculate that on your own. So pause the video and do that. Okay, for Q, did y'all get 0.0329? That is unitless. Be sure you remember that's plus. Don't multiply everything out here. I'm going to leave off the units because I'm running out of space. But notice I did use the kilojoule R. I'm going to break it down into steps. So I got 5.4 kilojoules per mole. I took the natural log of the Q, Ln, and I went ahead and multiplied it out. When I did that, I got negative 8.46, and then some numbers. And so for the delta G, I got negative 3.06 kilojoules per mole. So delta G is negative. So it is moving forward. It's spontaneous, so the reaction's moving forward to achieve equilibrium. The delta G confirms that. We could have also compared the Q to the equilibrium constant. Right? And since the equilibrium constant's larger, we also know that the reaction is moving forward. But both of those just confirm each other. We can also use the delta G to determine the equilibrium constant. Okay? If a reaction is at equilibrium, then that means that the delta G is 0 and that Q is equal to the equilibrium constant, K. So I kind of threw that in early. So we know that at equilibrium, we have this. And so if we just solve for delta G standard is equal to negative RT times the natural log of K. Okay, so the delta G standard can give us the equilibrium constant for a reaction. So use Appendix 2 to calculate the Kp for the following reaction. At 25 degrees Celsius. And I just realized when I started doing this that we did not talk about how to use Appendix 2 on the delta G. It's actually the same. You can calculate the delta G standard by summing up the Gibbs energy of formation of the products minus summing up the free energy of formation of the reactants. Okay? So the Appendix 2 has all of those values. It has the delta G's, the delta H, and the delta S. So what I'm going to do is use that formula, and I'm going to look these up in Appendix 2. Oh, that doesn't make sense, does it? Because this is supposed to be water. Let's redo that. 2 H2O liquids. Now that makes sense. Okay. So water delta G. And the hydrogen and oxygen in the appendix they should be 0 because they're elements. So the products is 0. So products minus reactants is 474.4 kilojoules per mole. That's the delta G standard because it's products minus reactants, which have a negative number. And so we're calculating the equilibrium constant. So 474.4 kilojoules per mole minus 8.314 times 298 Kelvin times the natural log of K. And I've got that the natural log of K is equal to negative 191.5, and I have to take the inverse natural log of that to get K. Whew, that is a tiny, tiny value of K, isn't it? 6.95 times 10 to the minus 84. Very small equilibrium constant, which we would expect. Does water at 25 degrees Celsius, does water start breaking down into hydrogen and oxygen? No. And a very small equilibrium constant tells us that that doesn't happen. And we're glad that doesn't happen. Okay. That is going to complete chapter 18. Yay. I'm going to select some end of chapter problems for you. These start on page 868. Your numbers 15, 17, 21, 31, 41, 45, 55, 57. That may be it, guys. That's all. That's all the end of chapter problems. We'll touch on chapter 19 for the next lectures this week, and we're wrapping it up. So next week you'll have a test on chapters 18 and 19. I don't have my calendar handy. Let me pull that up. That's going to be April 27 through May 1st. Also that week will be the final exam review. That's what I have planned for now. So next week you'll take a test and then you'll study for your final. And yeah, y'all need to. That's all we'll do next week. No new lecture. I'm sorry. No new lecture for next week. We'll do some Canvas conferences. If there's a best time for you guys, let me know.